This is Project MOAR, that's Mother of All Roombas. It's a 4 horsepower Harbor Freight Bauer Shop Vac that I converted into an autonomous Roomba style vacuum. I do want to stress that this thing is not necessarily meant to be a fully functional machine. I do not trust it to operate unattended, and I would not let it run in my house without watching it because it is somewhat of a fire hazard. It was a quick and dirty project, very short time scale, quick turnaround, but I got it to work. It does what it's supposed to do, and I had a lot of fun with it. The Shop Vac itself was around 60 bucks from my local Harbor Freight, and the only other thing that I bought for this project was the inverter for like $30 off eBay secondhand. Everything else, I was working with parts I already had laying around from past projects and future planned projects. I converted it to battery power, put an adjustable mount on the front for the original vacuum to suck up debris as it drives, and of course there's 2 big drive wheels added. The main structural elements are these laser cut plywood brackets. That's just 1/4 inch plywood, and they're all tied together with 1/4-20 threaded rods. The bottom one, the bucket rests on, and these short ones clamp it down on the top of those caster wheels. And the top one is pressed up against a ridge in the shape of the bucket itself. So the bucket is totally constrained. It can't come loose if it tips over. Pretty much everything else is 3D printed brackets that bolt onto the threaded rods. I gave it this uniform radially symmetrical bolt pattern just so that it could be modular and I could easily add and remove things as necessary. The brain of this project is an Arduino Uno with a custom proto shield on top that breaks out headers for all the different connections, so it's kind of modular. These are all the data lines going to the 2-motor DF Robot brush DC motor controller, with each pair of green wires going off to my motors. The wires right here from the DC-DC converter are the main 12-volt input, which also goes over to the power in on the Arduino. Got a 5-volt logic supply to here, and this is the mechanical limit switch. It also breaks out the female connector for my PlayStation 2 controller, which does not need all these 15 pins, but I already had the male connector on it from a different project. And these PlayStation controllers communicate with SPI, and I found that it's really essential to have pull-up resistors to get it to work reliably. Nothing special at all about the buck converter. It's just the kind that's usually made for golf carts and stuff like that. It takes 48 volt down to 12. The collision detecting bumper design works remarkably well given how kind of janky it is. It's made out of this bent coat hanger with a fishing line that runs up through part of the frame there and over to this mechanical limit switch. And the coat hanger is bent in such a way that it's kind of like a spring with some preload on it, so it keeps tension on the line and holds the switch down. But when I bump into it, it opens the switch, and it works if you bump anything anywhere on the bumper. The kind of weak point of this is if it hits at a sort of an oblique angle near the end, it won't trigger it very reliably, but for the most part, it works on flat surfaces pretty well. The big vertical part is just the extension that came with it. It's not actually doing anything but serving as a structural element to mount the tip to. The wheels are some 10-inch diameter wheels from Harbor Freight that are meant for like wagons and carts and things like that. They do have bearings integrated, but I'm not using them because the outer races are fixed to the rim. If I ran a drive shaft through it and had that fixed to the rim, then the bearings wouldn't really provide any kind of differential rotation or be of much use at all. So the way I mounted these is with these little laser steel plates that just use the same bolt holes. And this is a 2-part wheel, so I just take it apart and mount that. And then that profile in the center matches right up to my motor. These are 40-299 is the part number. It's a remanufactured windshield wiper from like a late 90s, early 2000s Ford car. And I really wanted to kind of characterize these a little bit and play with them with 2 on this robot, because I'm going to be planning to use 6 of these for an upcoming project in the future. These are the same motor, even though the casing looks a little bit different. I guess it's just from a different manufacturer, but all the mating features are the same. They're mounted on a flat laser cut plate with these existing threaded holes, and I have the wiring just with some spade connectors plugged in there. I reverse engineered the pinout of these 6 spade connectors. These 3 here are the main driving ones. That top one is the common, and then depending on whether you use the middle one or the third one, it'll run at 2 different speeds. So my guess is that that third one either goes through a resistor or it just doesn't connect to the entire length of the coil inside. And then of course you just reverse the polarity to change direction. So that's how the windshield wiper would get its fast speed, slow speed at the same voltage. And then the other 3 are basically limit switches at different positions. And I guess that's so the car knows when to turn the wiper back around, but I'm not using them for this application. It's also got this integrated worm drive gearbox, and you can see there are the contacts that kind of act like the limit switches, so it knows where it's at, but that gives it plenty of torque. It's around 80 RPM or so under no load, and it draws in the range of like 3 or 4 amps. In a future project, I'll be using these more continuously at a higher speed, so I may even try to use those contacts almost like a rotary incremental encoder with a very low resolution to get some speed feedback. And there's the 1/4-inch plywood laser cut mounting plate, along with some 3D printed brackets that hold it onto the exoskeleton. I do have a 30 amp fuse coming right off the main positive line for where the battery connects. And the reason all this wiring harness looks like a bunch of weird mix-matched connectors and wire gauges and labels and stuff like that is because I took it off an old e-bike project that I built and modified a few things here and there to make it work. The main power switch is also taken from that e-bike, which is why this mount does not look like it's meant to mount here, because it isn't. And the reason there's 2 switches is just because the full battery load runs through it, so each individually was not rated for the current, but in parallel they can each take 15 amps. The battery slides right in here and actually rests on one of the original caster wheels. This is an extremely sketchy Chinese e-bike battery. I wanted this to be easily removable because this is a really sketchy battery and I want to put it in a fireproof box before it burns my house down. This enclosure houses all the load resistors. It's an off-the-shelf project enclosure from Radio Shack, of all places. I just drilled a bunch of holes in it for some air ventilation, but clearly that wasn't quite enough. And the vacuum's original power cord plugs in right there, then runs down through the load resistors. I did not make any irreversible modifications to the vacuum at all. No wires cut, no holes drilled, nothing like that. The input to the load resistors is the output coming from the inverter. The inverter is just some piece of junk off eBay. Got it used for cheap. I think it was used in a car for a subwoofer. This is what limits the power I can provide to the actual vacuum motor. It's rated for 1,000 watts, and it does have a feature, a self-cut-off thing when the current draw gets too high. I don't want to pull more than 1,000 watts anyway because the battery is only rated for a continuous discharge of around 1,500. So that's why I needed the load resistors to just reduce the current draw and sacrifice a little bit of motor power in the vacuum itself. I did do a little bit of code to simulate the power consumption because I knew that motor draw was going to be an issue. So slapping those load resistors in there was not just totally willy-nilly. I plotted the draw based on the motor duty cycle and the resistance of the load resistors, and I needed to keep this below around 1,500 watts. So I did actually measure with a multimeter some data points to get this relationship with the load resistance and the current draw, It is not just as simple as plugging in Ohm's law and hoping for the best, because it is an inductive load with resistance on a AC source. It was a little bit hard to calculate that, so it was easier to just measure real values. Plus that takes into account the inefficiencies of the inverter and all of that good stuff. But anyway, I was thinking I might need to reduce the motor speed to cut the current draw down there on the drive motors, that is, for this. But that power consumption is honestly just about negligible compared to the vacuum motor power consumption. So I ended up settling on 6 ohms. And just with the original switch, I can turn on and off the vacuum and run it separately from the motor drive and the rest of the electronics. This is the big laser cut base plate and the original 2 caster wheels. There were 2 more which I removed. They're just held on with 1 little screw to make room for my driven wheels. And I can adjust the motor mount, the 3D printed parts, up and down on the lead screws to change the relative height between the casters and the driven tires. I intentionally have the driven wheels a little bit lower than the casters, inspired by those Home Depot lumber cart designs, and that's so that I always have 1 caster barely off the ground and keep all my weight on the drive wheel. This is my CAD model. It is certainly not complete. I didn't really bother being more thorough than I needed to be to make all the parts I was making, but a couple of interesting things to point out. These motor mounting blocks, the motors themselves are asymmetrical, as are their mounting plates, and so the reason there's unused holes is just so the same part works in all 4 positions. Didn't want to design another unique part if I could get away with not doing it. I did not model the motors themselves because I didn't really need to. I just modeled their bolt pattern, and this bolt pattern is designed such that it's still fully constrained, even if I made a slight measurement error and 1 hole is a little bit misaligned, it still holds it constrained. And this cutout shape lets me drop the motor out and down without disassembling this plate or removing these, because when the wheel's on it as well, it's really hard to get to these bolt holes. This is the first ever manual test drive. I was using the PS2 controller, and you'll notice I have the fire extinguisher at the ready there. The PS2 controller is for testing purposes and so that I can move it around without carrying it. It's just like tank style steering with 1 wheel on either of the 2 sticks. It does not go nearly that fast in auto mode. I slowed it down, but this thing can go like 7 or 8 miles per hour. I do have built in some logic that ramps the motor PWM up and down gradually rather than sharply, instantaneously adjusting it so that it doesn't draw too much current. It can do a burnout, in case you were wondering. This is an early test of the auto driving mode with the bumper switch active. It works really well in this little kitchen area where there's no big obstacles and all the walls are nice and flat. Coming up here, it does hit the wall at an oblique kind of angle, and the other wheel that's not against the wall makes the robot kind of turn into the wall and activate the switch. So in this case, it can actually operate nearly endlessly without ever getting stuck in an ideal situation like this room. At the end of that last clip, it kind of got trapped in a loop bouncing off one wall and then the other directly opposite it, just going back and forth between two parallel walls. So after seeing it do that, I added a little bit of randomness into the amount that it turns, so it's not just a perfect 180-degree turn every time, and it won't get trapped in a situation like that. The code's pretty simple, but just thought I'd run through it real quick. Just initializing pins, typical stuff. It reads the PlayStation controller. If there's not a controller connected, these functions are the auto driving ones. This one checks the bumper switch, and this is just straight driving like it sounds. Inside this function, that also includes some of the manual control stuff. But the bumper function is essentially some sequential open loop controls that just sets the motors at predetermined speeds to do like a reverse, a slight turn, and then drive forward again. And there is some randomness in how much it turns. Just some kind of test prints for troubleshooting, constant variables, fun stuff. And then the motor control functions. This basically takes the throttle that I like to keep it in my code as like a 100 to negative 100% type of thing. That way if I change motors from something like a brushless with a ESC to what I'm using here, just a regular brush DC with a 255 PWM, all I really have to change is this, and then the rest of the control logic stays the same. The adjust motor function ramps the PWM up instead of instantly changing it. Pinout. This is the stuff that reads the controller. It's pretty much all taken bits and pieces from the examples in that library. And the straight drive function, pretty advanced stuff right there. Also, map targets in this motor control tab is what converts the PlayStation controller values into motor throttles. And then at the end of the PlayStation tab, this function just looks to see if there's a controller connected and adjust the motor to the throttles determined by the map targets function. The rest of these tests were done with the vacuum actually on, cleaning the dirty floor in my garage. So for the rest of the clips, I'll probably cut the volume down so you don't have to listen to the vacuum noise the rest of the time. Here's an example of it stuck in a spot where its motion is blocked, but its bumper switch is not actually hitting the obstacle. In these cases, I can just manually pull the bumper switch and then it's on its way again. Here a tiny pebble got jammed under one of the caster wheels and actually got the robot stuck because there wasn't enough weight for traction on the drive wheels. That's exactly what I was trying to avoid with the Home Depot cart style center wheels lower. I could mitigate that odds further by even lowering the drive wheels more. But right around this point, I started to notice some smoke coming out of the load resistor enclosure. I'd been periodically feeling the battery to check for any excess heat, but I did not think to look at the actual load resistors. I put as many resistors in to get an equivalent resistance at 6 ohms as I could. That would mean less heat dissipation for every individual resistor and more surface area to dissipate that heat. So I didn't think it'd be a problem, but my early testing, I'd only been running power through them for like a few seconds at a time. So clearly it got hot enough to start melting some of the insulation on those wires. It also melted some of the plastic enclosure, and that's where the smoke was coming from. You can see those holes used to be circular, and it even poked through the enclosure at one point right there. Everything still works, but I decided to end the testing there. Some improvements to be made if I were to start this over. Generally, the very narrow width of the vacuum tool compared to the wide wheelbase makes it really hard to get complete coverage over a large floor area. And the wide wheelbase also makes it prone to running into things and kind of turning into them, especially given that the bumper switch is not as wide as the wheelbase. It does occasionally find itself where an obstacle blocks its movement but doesn't trigger the switch, causing it to get stuck. And if I were to do this over again, I'd probably scale it down to a less powerful Shop Vac. That would have saved me a lot of trouble dealing with load resistors and the high throughput power electronics required to drive that 4 horsepower motor, which I think is nominally like 2,700 watts, something like that. So this was a really fun project for being a short-term thing that's kind of slapped together. But anyway, now I'll probably just return that vacuum to Harbor Freight. I won't tell them it spent some time as a robot, and thank you for watching.